Okay, so today we're going to talk about a couple of loose ends here. The first thing we're going to talk about is ionic radius. All right, so we've studied the radius and we know the causes for the trends for radius. Right, we talked about how when you go left to right, the radius decreases because the effective nuclear charge is increasing. We talked about how when you go down in a family, the radius. Let's see. So when you go left to right, it gets smaller. And when you go down, we know they get bigger. And the reason for them getting bigger when we go down in a family is what? More energy levels. Yes, more layers. Okay. So let's talk specifically about then when you have ions. Well, whenever you have an ion, the radius is going to change. Right? So in general, we need to understand that cations are smaller than their atoms. Because cats are dainty, right? And they can twist and turn if they jump off buildings. No, it's because cations are positive ions, and positive ions means they lost electrons, right? So, first two families. If I look at lithium, here's a normal lithium atom, and here's the lithium ion. That's a significant size difference. So we have to ask ourselves, what happened when lithium became an ion? Well, lithium was 1s2, 2s1. And so its valence electron is this guy. Right? And valence electrons are the electrons that can be removed. So when we lose that second energy level, it's like going from this to this. So cations get smaller, right? They lose energy levels typically. And we can make the same case for sodium, for potassium, for anything down in this family. Okay, let's look at group 2, the earth metals. Here's beryllium. Here's the beryllium ion. You can just draw a very similar picture here. Right? Beryllium is 1s2, 2s2. And losing those two valence electrons, which would be here, right? They would be here. So we would end up with just that. And yes, of course, it's smaller. It no longer has two energy levels. It only has the one energy level. So first of all, do we understand then when we lose valence electrons, we're losing energy levels? Okay? All right. Same thing, same argument can be made here. For aluminum, going to aluminum ion, +3, right? Okay. Now, I guess I should talk about the in-between state. So in group 2, what if they don't lose both valence electrons? All right, what if they only lose one valence electron? So instead of having 2 electrons being lost, let's say this happens, and we go to the intermediate. So 1s2, 2s1. So this reaction here reflects the ionization of one electron. Okay, but the one electron that's pulled off and the one electron that remains, we are still going to be smaller even though that second energy level is still there. And the reason why this particular, the Mg+1 ion, I'm sorry, I keep saying Mg, this is beryllium. Even though the beryllium +1 ion has its second energy level, the reason why it's going to be smaller is because it does not have repulsions within that first, or within a second energy level anymore, right? So over here, you had 2 electrons, 2 valence electrons in energy level 2. But you pull one electron away, and now you have the sole electron, the only electron in energy level 2. There's nothing in energy level 2 to repulse it. So since it is not clashing with another electron in energy level 2, the range in which it travels around is not extended anymore. It doesn't have to fly around and avoid and bump into anything. It's got a cleaner path. Imagine if you were running around a track and you were the only one running, could you choose to run in the inside track? Yes, you could, if you were the only one there. But if there were other things there on the track, you would have to swerve around them, right? And so that means the total volume of area that you're going to be moving around in is larger if there's other things there, right? And so when there's multiple electrons in the valence shell, they repel each other, they bump into each other, and so they take up more space. So we lost one electron. This is smaller. Now, if we were to remove the second valence electron, well, of course it would be smaller, right? But this would be a dramatic energy change, or a dramatic change in size. Whereas from here to here, right? So small change in size. From here to here, dramatic change in size. Because anytime you lose an entire energy level, that is always a much, much larger change in size than if you just make the energy level a little bit smaller. Does that make sense, guys? Okay. All right. And the same argument can be said for aluminum, because aluminum, in order to become +3, it would have to go aluminum +1, aluminum +2, lead, and aluminum +3, right? Okay. Let's talk about anions. Anions are larger than their atoms. Remember, anions are negative ions. They are larger. Why are they larger? Well, what is happening to these atoms? They are all gaining electrons. Let's take oxygen, for instance. Here's an oxygen atom. You give it an electron, it's going to swell. You give it another electron, it's going to swell yet again. So this is O-2. The reason for the swelling is the additional electrons that are repelling each other. So the opposite reason for what I just described. Now, distinction, though. When I add electrons to oxygen, right? So if oxygen here is 1s2, 2s2, 2p4, and I add an electron to it, the new valence electron configuration, or the electron configuration, becomes 1s2, 2s2, 2p5, right? And then if I add an electron to that, becomes 1s2, 2s2, 2p6. So this is the electron configuration for O2-. In the process of adding electrons, did we increase the energy levels? We did not. Okay, we did not increase energy levels. We added electrons, there's more repulsions taking place, but we are still within its original energy level. Okay, so that's one of the main differences when you're forming ions. If you're talking about the metals, when metals form ions and become cations, they lose electrons, but they could lose entire energy levels. The nonmetals cannot do that. They cannot change entire energy levels. They can just gain electrons, but they still stay within the same energy level. Okay? All right. In a typical ionic compound, anions occupy most of the space. So in an ionic compound, for example, NaCl, what do we really have in NaCl? We have the Na plus ion and we have the Cl minus ion. Well, Na plus, in order for sodium to become an ion, it must have lost its third energy level. So it shrinks dramatically. When chlorine gains electron, it swells. So even though both of these are an energy level 3, there's a dramatic size difference between sodium originally was in energy level 3, but after losing its valence electron, now only has 2 energy levels. All right, so which one of these is the chlorine? Which color? Yeah, the green, right. Okay. All right, so That's ionic radii. Oh, I guess I should go back one more thing. So lithium, if this is the size of the lithium ion, this is the size of the sodium ion. If this lost an energy level and this lost an energy level, then it still stands to reason that sodium is larger than lithium. Because how many did lithium have initially? 2. And by losing one energy level, now it has 1. But sodium, how many does it have initially? 3. And by losing 1, now it has 2. So you still have more energy levels in sodium than lithium, even though they both lost an energy level. Sodium still has more. And so that's why the size of ions will still reflect an increase as you go down. Okay. All right. And then likewise, in a similar logic, notice that we have the nitride ion, N3 minus, O2 minus, and F minus. This is all period 2. But notice that the size still decreases from left to right. They all have gained electrons. Yet the size decreases to the right. What is the fundamental reason why the size decreases towards the right? The effective nuclear charge is still higher as you go to the right. Fluorine has the highest effective nuclear charge here, so that's why it's drawing its electrons in the closest. Okay. Now, another term we could apply here that might come up now and then is isoelectronic. And that is when the same number of electrons are present. Okay, so N3 minus, O2 minus, and F minus. Those are considered isoelectronic. All right, if I said, how many electrons does N3 minus have? It's nitrogen, but it has 3 additional electrons. So how many is that? It should be 10, right? Nitrogen has 7 on its own plus 3, so it's 10 electrons. Oxygen has 8 on its own, but plus 2 electrons, so it's 10. And fluorine has 9 on its own, but plus 1 is 10 electrons. So these all have the same number of electrons. If they have the same number of electrons, but they have different numbers of protons, it makes sense why their sizes are not the same. The more protons there are, that's a higher nuclear charge. That's a stronger attraction. That is why F minus is the smallest. Does that make sense, guys? Okay. Another example. Oh, Mg2 positive, F minus. All right, so magnesium ion or fluoride ion, which of these is larger or smaller? Well, let's compare this. They're both ions, and the term I just brought up was isoelectronic. So if you counted the number of electrons, you can see where I'm going with this. Magnesium has how many electrons? In this case, the ion has how many electrons? 10. And the fluoride ion has 10. So they both have the same number of electrons. What is governing their size? What other subatomic particle would be useful to talk about right now? Okay. And so magnesium has 12 and fluorine has 9. So which of these is larger? F minus. F minus is larger because they have the same electron configuration, but the one with the most protons is attracting electrons inward more. Okay, so something like that. And there's going to be a lot of comparison questions. And when you're answering comparison questions, you have to find the commonalities, but you also have to focus on the difference. Right? When you're talking about sizes, it's very important to understand the electron configuration structure of the two things that you're comparing. In this case, we realized the electrons were the same, so the primary reason for a difference is the nuclear charge, the protons. Okay. Photon Electron Spectroscopy. So we have talked about ionization energies, but so far all we've said is, oh yeah, it's the amount of energy needed to remove an electron. Well, how were ionization energies determined? The answer, photon electron spectroscopy. So the idea is this. If we shoot high energy X-rays or photons, right? Because an X-ray is just a high energy photon. If we shoot high energy X-rays at atoms, we'll be able to knock electrons off. So imagine you have an atom and you're shooting an X-ray at it. The result of this is that an electron is going to be knocked off, right? You're going to have an ion, and here's the electron just whizzing away. So when we calibrate the machines to shoot the X-rays at the atoms, the energy is known of the photon. We know this because we're the ones dialing up the instruments and deciding what frequency and energy to have. And then the electron that's knocked off, this electron's energy can be determined. It can be determined a number of ways, either through by a color or through by a detector, which senses electrons as they collide with it. So the point is, this electron energy is known. So if we know the energy coming in, and we know the energy that the electron has after it gets knocked off, the difference is how much energy was holding that electron on, i.e. the amount of energy needed to remove it. So the energy of the photon is equal to the sum of the kinetic energy of the electron and the ionization energy. And since this is what we're trying to find, we rearrange to solve. We can find the ionization energy simply by subtracting the kinetic energy of the electron from the energy of the photon. All right, energy is conserved, so you can assume the difference. That's the reason. So, first example, an atom is hit by a photon with this much energy. Okay, so this is the photon energy, E. The ionized electron has this much energy. This is the energy of the electron. What's the ionization energy? We subtract. So subtract. I don't want to do that in my head. Let's calculate that real quick. Okay, so in this case, the ionization energy is 28.6 megajoules per mole. It's just subtraction, but you got to know what numbers to subtract. Are you guys okay with that? You shoot energy. You shoot an X-ray at something, and you find the energy of the electron, and they subtract. Okay, that's it. All right. So, what kind of experimental results do we see when this happens? So, when we shoot X-rays at an atom, depending on how many electrons the atom has, right? Imagine just like shooting X-rays at this thing. You're going to have electrons jumping and being knocked off from various levels. So we can't just aim at one electron in one level and only try to knock off electrons of a certain level. You got to kind of you're bombarding this, right? And so the result is we see all of the electrons come off. Now, depending on how many electrons it has, that changes the way we see the data. So, in this first graph here, we see a bump, and what we're graphing here is, on the y-axis, is relative number of electrons. On the x-axis is ionization. This is the ionization energy after it's been calculated, okay? So, here we have a single peak. The fact that we have a single peak means all the electrons that were knocked off, if they all have the same ionization energy, that means they all came from the same place. They all came from the same subshell. What elements have only one subshell? Yeah, right? The 1s, right? Hydrogen and helium. Those are the only two elements that have 1s. Now, I can't tell if this is hydrogen or helium, because what we're graphing here on the y-axis is the relative number. All right, so because I have a sample of hydrogen and of atoms or a sample of helium atoms, as I shoot electrons on there, this is my one piece of data that I get. I can't tell if there are atoms that have 2 electrons coming from the same atom, or if these are just a result of electrons coming from several different atoms. Okay, so we'll revisit that thought in just a second. Okay, so if I run this trial again, and if this is what I see here, right? So I see again one spike, right? And this element that we're seeing here, it cannot be lithium. I know that because there's only one spike. And if there's only one spike, what does that mean?
It only has one subshell.
Yes. Only one peak equals only one subshell. All right, so what we're establishing here is that the number of peaks that you see is the number of subshells. Okay, so let's, I should also mention, if you note the energy on the x-axis, okay, so the energy, it's graphed a little differently, but we have higher energies to the left, closer to the y-axis, okay? And so the lower energies are farther to the right. This is not always the case. You have to be careful. You have to pay attention to the values because sometimes you see this reversed, where it's low on the left and high on the right. Okay. Let's take a look at a slightly different diagram here. So let's say that a similar experiment is carried out, but this is what we see. You should recognize this because we have shown you an orbital diagram that was set up similarly. What do you think this is telling you, this picture here?
Electron configurations.
Electron configuration, and why are there different lines? Where are there lines in different heights? What does that mean, you think?
The jump in energy between the subshells or sublevels, subshells is relative.
Okay. So if I were to give this first one here a name, what subshell do you think that would be?
1s.
Okay, so now there's two. There's two that are grouped together. What do you think that is? It's called 2s? Oh, okay. Well, then what else is there in energy level 2? 2p. So really what you're seeing is 1s2, 2s2, 2p1. Okay. So if we were to sketch a PES diagram, how many peaks would it have for this data? It should have 3 because we just said the number of subshells is the number of peaks, right? Should have 3. Describe the relative height of the peaks. So remember, height. What does height mean? Height on a PES spectra is relative number of electrons. So if would all of these peaks have the same height? No, they would not, because they would only have the same height if what?
They all have the same number of electrons.
If they all had the same number of electrons, but they do not. So make a rough sketch. And we're going to keep with convention with the other diagrams in these notes that the high energy is towards the left and the low energy is towards the right. So we've established we have 3 peaks, right? So high ionization energy or low ionization energy. We have the subshells 1s, 2s, and 2p. Of those 3, which one do you think would require the most energy to remove electrons? The 1s. So the 1s peak, let's put here. Okay. So after 1s comes 2s. 2s. Does 2s have the same number of electrons as 1s? So it should be the same height. Actually, I'm going to move my writing. I'm going to write this 2s here. 2s. Okay. Now, there's a third peak, 2p. 2p is partially shielded by the 2s, which means removing electrons from 2p is slightly easier than removing them from 2s, which means it's going to be nudged over nearby. And you know what? I'm going to make it half the height. Why? There's only one electron there. Number of electrons on the Y. Okay. So let's look at this next example. How many peaks do you see? Oh wait, we didn't answer the question. What element is this one here that we just did? We just drew this one. What element is that? Why do you say that?
Because it has an configuration 1s2, 2s2, 2p1.
Yes, boron. Okay. Problem 4. Assuming that the first peak is n equals 1, so energy level 1. So following the convention, they're telling us that this is 1s. Sorry, that green is not showing up very well. Let's use darker color. They're telling us that this is 1s. Okay. This would be 2s. What would this next one be here? 2p. All right. So if this relative height is 2, it stands to reason that this is the same height. How would this peak compare to the others? Roughly.
3 times as big.
It looks like 3 times, doesn't it? Because if I doubled the first one, if I doubled this from here to here, wouldn't doubling that bring it to about here? And so it looks like then really the third peak is about 3 times the height of the original. So it would be reasonable to say that there's 6 electrons here. So 1s2, 2s2, 2p6. So it would neon would be a reasonable guess. Okay. Making a similar assumption as in problem 4, which element is this PE spectrum likely of? So take a look at that and see if you can come up with it. It's problem 5. Which element is that? What do you guys think? Eva, what do you think that is? Yes, I'd say that's magnesium, right? Based on what we know, the first peak, first of all, do you understand that I know this first peak is full? How do I know that this is full? Based on problem 4, but also the fact that this has more peaks. Right? This could not be partially filled if more peaks exist, right? Because you have to fill the lowest energy levels first. So if there's a subsequent peak, that means that all previous peaks are full, right? Aufbau principle. So I know that this must be 1s2, and this must be 2s2, and this must be full at 2p6 because another peak exists. Now, this last peak here, do I know if this is full or not? I do, and why? What would be the deduction that would lead us to know that this is full as well? It's the same height as the other ones. right? And we know that 3s follows 2p, and since it's the same height, it has the same number of electrons from that subshell. So that's our electron configuration. 1s2, 2s2, 2p6, 3s2, which is magnesium. Okay, so as you can imagine, if we were to have any element undergo photon electron spectroscopy, based on the peaks, we could identify the element, right? And if you could even identify ones that are close to each other if they're off by, 33 and 34 electrons, right? Because we understand that each one of these peaks represents a subshell. Okay. So, how many peaks would a PES spectrum of carbon have? Find carbon, maybe write out its electron configuration if that helps you. How many peaks would that have? Yeah, it should have 3. There are 3 subshells. Would they all be the same height?
Yes.
Don't they all have 2 in them, right? Yes. Yes. So if we drew this one, it would look something like this. Follow? The 2s and the 2p are close to each other. Why are they close to each other? Same level, yes. Would the PES spectra for a magnesium 2+ ion and neon look the same? Ron?
I would say no.
They would not. You are correct. They do not. Why?
So they are isoelectronic species, but Mg2+ is a higher effective nuclear charge, so its peaks would be further to the left. It would take more energy to remove the electrons.
Yes. If it's got more protons, it's going to require more energy to remove. So let's just do a color-coded chart here. Okay, so neon, 1s2, 2s2, 2p6. Okay, there's neon in green. Magnesium, with a greater effective nuclear charge, more protons. Remember that we said that high energy is to the left and low is to the right. So therefore, since it's a stronger pull on all of its electrons and subshells, we're going to see a shift. Greater energy to remove electrons from the magnesium ion than from the neon atom. That makes sense, guys? Okay. And last question for the day. Would the PES spectra for chlorine 35 and chlorine 37 look the same? These are 2 isotopes, right? So remember what the difference between isotopes? What is the difference? Neutrons, right? So neutrons and thus mass. Was there any discussion about isotopes and electrons? No, we don't ever really talk about electrons when we're talking about isotopes. We're only focused with neutrons. So, would these 2 look the same if we drew PES spectra for both of them? Yes, they would. You could not use PES to determine the difference between the different isotopes because they have the same number of protons. All right, we're not going to talk about electron affinity. We are out of time. We'll have to pick up that later.